Hello there. Hey guys. So this is my first live stream on YouTube, and my only concern is that my internet is just gonna die at some point. So if the live stops, probably it's my internet. So do we have someone here? I never use this interface. So yeah, we have two people online. So say hello. So here today I have this HP-410 voltimeter. It's a very neat instrument, and I received it like this evening from mail, and I already removed the covers. Hello, Andrew. And yeah, so I ordered some capacitors to replace the power supply capacitors. And if everything goes well, we maybe are gonna align this instrument afterwards. So the first order of the day is going to be to replace the capacitors. And yeah, so I was actually cleaning the instrument inside. I have a few spots yet to clean. So I'm gonna show you guys first a little bit the instrument itself, and then we go through the process. So a few things about this multimeter. So this is a totally analog multimeter, and it's a tube multimeter. It's actually a hybrid. So this 410C multimeter, originally the version A and B, they were totally tube-based. But this C revision that was the latest one for this equipment, HP changed the circuit, and it has only one tube. And this tube is responsible, it's basically two triodes, if I remember correctly. So the first triode fits like the input for the chopper amplifier, and then the second triode fits the output. So basically they kept the tubed characteristic on the instrument, and all the tubes in the middle for the amplifier, they substituted for transistors. So they kept the characteristic of the instrument, but they made it cheaper and easier to maintain. Also, another benefit of this older revision was that they basically eliminated the selenium rectifier from the older power supply, and now they just use plain diodes and a simple linear voltage regulation. So in the end, I believe that the power supply is also more dependable. So yeah, so let's go through the instrument. So I'm gonna place here the board so I can show you guys how it was when I got it. So let's go through the interface first, right? So something that is very nice on this instrument, the revision A and B, they had a smaller dial here, and it wasn't even colorful, the lettering, and so now it's way better, I think, to read the information. And also they moved two of the buttons to the back of the instrument, because I believe with this redesign, and after we can go through in the schematic of it, they've made the instrument more dependable. So we only have here this red button that is the AC zeroing functionality for the instrument. The DC zeroing and the on zeroing is in the back of the instrument now. So yeah, so the engineers, they realized that it wasn't really necessary anymore. This instrument, it has different probes for each one of the functionalities. So let's go here from the beginning. So the first red wire that we see here, that someone puts like a alligator clip, is for ohms and for DC current. Okay. And one thing that is neat about this instrument is the fact that it uses coaxial cables. So this is not our standard multimeter like silicon cable. It actually is a coaxial, really to reduce as much as possible the noise inputting in the instrument. The second one is our common. So is basically our common ground. And this instrument, there is something that is very crucial if you decide to have an instrument like this in the future. That is the fact that this common is not isolated, is connected to Earth. So, for example, if you want to measure your mains line, you cannot connect this, on a phase. For example, you cannot switch. Okay, if you have like 100% sure where's your neutral, you could connect this, but otherwise you're gonna have a dead short. So if you wanna measure AC with this instrument, never connect this. Only connect the probe itself, the positive of the probe, so you don't short your instrument. And this probe here, the gray wire, is for the DC measurement. This instrument is one of the features of this instrument that is very interesting, is the fact that it can go up to 1500 volts. So it's way over your average multimeter, even those handheld multimeters, usually you can go maximum a kilovolt with them. This instrument goes to 1500. So it's a pretty neat characteristic, especially if you work with high voltage circuits, RF amplifiers, anything like this. And the last but not least, and is one of the most special parts of this instrument, is these things like this, where we connect here. And this is the AC probe. Okay, it only works with AC, this probe. And here there is an additional tube. So I told you initially there's only one tube, but inside, but then we have this tube here that's basically a diode. And this probe can measure up to 300 volts and can go up to 700 megahertz. So basically, for people that work with RF design, for example, you want to develop a RF power amplifier, you can actually measure your output with this probe up to 300 volts, of course. So, and people say that this probe goes calibrated to 700 volts and can go up to 1.5 gigahertz out of the calibrated range. So it's really remarkable what this instrument can measure, and you really can't find this in any other normal digital multimeter. So this is basically the main characteristics of the instrument. Let me show quickly the back of the instrument. So here in the back, we already have the new IC connector. That is the same power connector we use in computers nowadays. And then we have our zero adjust for DC voltage. And we also have the ohms adjust here in the back. And we also have a DC amplifier output. So because this instrument, it basically has an output from the amplification stage itself. So let's say that you wanna daisy chain this to, for example, an ADC to make some kind of acquisition. So you could, for example, use your AC probe measuring RF in high voltage, and using the outputs here to make some kind of acquisition. So very, very neat feature, especially if you wanna automate things. Okay, so let's go now. I hope that the video quality is good. So give me a thumbs up on the live chat if the audio and the video quality is good. I'm using a webcam here because I don't have a capture device for my Luminix. So it's what we're gonna have for today. So I'm gonna twist the instrument right now so you can see here. So starting here in the back, so we have a very tiny transformer, and this transformer, it was reduced because now we basically only have 2 tubes instead of the 6 of the B revision, if I remember correctly. So we have much less filaments to feed, and the instrument itself really doesn't consume a lot of power. We have those 2 big capacitors that we are gonna be replacing today. One of this blue one, this Mallory capacitor, is a single unit, but I'm almost sure. No, sorry, it's 2 units. So this here is two capacitors inside, and this aluminum one we have 4 20 microfarad capacitors. So I have 6 capacitors here that we're gonna be substituting this tonight. Then we have the brains of the operation, that is the chopper amplifier. And now I'm gonna remove this board. I'm gonna show you guys in detail. So this is basically the heart of the instrument. And this uses a very interesting chopper architecture from HP. And it's basically a optical chopper, because what they do is, you see this block here. So this is a metal block, and this sensors here, they have 4 sensors. They are basically LEDR or photocells, if you say. And here inside we have 2 neon bulbs. And those neon bulbs, they are basically a relaxation oscillator. So they keep switching between the 2 neon bulbs. And what happens is, in one stage, it makes the acquisition for the chopper, and then it releases it, and then it provides the output. So we have the chopper effect. And so this was basically the beginning of the modern chopper amplifiers that we know. So basically an optical chamber here that makes the switching between inputs and outputs. And as I said, HP neatly, they substitute the additional valves on the chopper amplifier itself, and they only kept this guy here. And as you can see, they installed here a shield for the tube, and this tube has 2, I believe, are triodes inside of them. One is responsible for the inputs, and the second one is responsible for the outputs. And the inner amplification of the chopper is made by this, I think, or if I remember correctly, were 3 transistors, but I can see only 2 here. So I guess so are 2 transistors. And another advantage of this model as well is that you can see that basically we have Sprague poly capacitors all around the instruments. So if you want to make a recap of the instrument, will not be a big deal, because you basically only need to replace the power supply once. So this is our brains. Another thing that is interesting to see here is that they have standoffs. They have these blue standoffs because this is a very high impedance instrument. And this is another characteristic of this instrument. Afterwards, we're going to have a look into the schematic to see really what is the total input impedance of the instrument. But the B version was over 100 mega ohms. So if you really need to measure like very sensitive circuits, this is the kind of instrument you would like to, because with over 100 mega ohms of input impedance, basically you're not gonna bring any parasitic effect to your, especially RF circuits. Okay, and then, so this is the brains. We have an additional board here that basically has all the adjustments. So yeah, so we have the trim pots, we have the AC, half a volt AC, 1.5 volts AC, then we have 15 to 500 volts AC, DC, and 5 volts AC as well. So these are the main adjustments. Then here we have our selectors, right? So functionality selector. And on this side, we have our main range selector with a bunch of resistors here that provides us our division network. And they have a massive, I think you can't see, guys, here, but they have a massive glass resistor here. Usually they use this kind of resistors for like a giga ohm or something like this. So very dependable component, and they made this thing this way because, yeah, for like a giga ohm, any humidity in there would already provide leakages. So they seal the resistor inside the glass bead. So a very expensive resistor if you need to buy one of those. And here they have this additional board that is basically an interconnection board. They have a few resistors here as well, but it's basically connecting our power supply with the instrument itself. And here in the middle, they have basically the socket for the chopper amplifier. So acquisition from one side, and then we have power supply from the other side. Of course, we have the trim pots that are on this side as well, and the output. So yeah, so they provided this internet connection board that made the instruments very clean. So I like this this design. So now starts the less talking and more action, where I'm gonna be replacing those capacitors here. So just give me 10 seconds. I'll go to my bag to get the schematics, and then we're gonna have a look there as well. Okay, so I printed the parts that are interesting for us. So I hope that it has focus, but anyway, so here we have our inputs, and then basically we have our switch, we have our indicator needle inside the switch, and we have 150 and 230, so bivolt instrument, very handy. And then we have our main transformer. And as you can see here, the earth is connected to the instrument chassis. So yeah, so this instrument is referenced to the chassis. Another thing that is interesting to see on this instrument is that we have shielding between the primary and secondary. So the HP engineers, they really looked into noise suppression on this instrument. And as you can see here, we have basically 4 diodes, and then we have our electrolytic capacitors. So here we have our group of 4 20 microfarads capacitors, and those I'm going to substitute then with 33 microfarads. I decided to go a little bit over because, yeah, it's filtering, so filtering is always good. And so yeah, so I'm gonna put a little bit bigger capacitors. And for the second one, that are 1200 microfarads, I'm going to substitute for 2200, because nowadays we only have 1000 and I didn't want to go lower, and the next one is evidently 2200 by 25 volts on this case, and the 20, they are like 450 volts, and originally was 450 as well. So this I'm keeping the same voltage. Of course, those are like 150 degrees capacitors, Nichicon, the best your money can buy, right? Like those capacitors, if I remember correctly, they are like 4,000 hours. So yeah, basically I'm gonna die and these capacitors are gonna be alive. And this is usually how I like to replace the capacitors on my instrument. So I'm gonna be working now on this part of the circuit. So I'm gonna get a little bit quieter. If you have any questions, guys, just don't just watch, but send me some questions and we can rambling about the things. So I'm gonna start first here with the Mallory capacitor, because it is the closest one and the easiest one, I guess. And I think also I'm gonna remove this aluminum frame here. So let me get my posit drive, screwdriver here, and remove this frame. So this way I'm gonna have a better access to the instrument. I really hope that my internet keeps stable. I have been planning to make live streams for a while, but since that the malware started, like internet in Germany here got like very crappy, very much crappy, and yeah, so I wasn't confident enough actually to do a live stream, because I was afraid that my internet would like shut down in the middle of the live stream. But yeah, then I decided, okay, let's give it a try. I hope that it, yeah, missing one here. Let's see if it's gonna be enough. Yeah, great. So now I have way better access. You know what? I could actually remove this. Yeah, I'm gonna do it. If I just remove those, I guess, 3 screws here, I can move the back plate from away. And what is holding you, baby? Okay. It's a very easy instrument to tear apart. So yes, but there are some resistors here that are holding me back, but I guess it's gonna help a little bit. So now I need to bring my iron to the table. JBC, beautiful iron. And let me grab, I'm gonna get the instrument cable and use it. Hello, what's up? Now I can get some lead-free solder. My leaded solder that I love doesn't exist anymore because I consumed all of it. Now it has some tabs here that are twisted. So I'm gonna carefully untwist those tabs, because then I can remove the capacitor from the top side. One of the tabs has solder, so I'm gonna need to remove that solder first. Or maybe I'm just gonna cut the tab away, because yeah, I really don't care about the old capacitor. And yeah, thank you so much. Yeah, but to be honest, I am not putting enough effort on the channel, and I really appreciate your compliments. But yeah, I should be posting more videos. It's just because I have this perfectionism problem, and I I really like to to go deeper on the subjects when I make some videos. So maybe with this live stream format, I could do things like in a more relaxed way, where I don't need to care too much about preparing a script and then recording, because I guess when I'm just talking like this in an informal way, I can actually speak better, because yeah, I am not an English speaker, as you all know. And yeah, so for me it's really hard when I really needed to write a script, and then I needed to read it and make it perfect, and then I spend a lot of time. So in the end is kind of like a hello DEFCON. It's kind of like a stressful process, but I really like to share knowledge with everyone, guys. This is something that makes me really happy, and the reason that I post videos sometimes on YouTube, because I really like to give knowledge. I'm basically a self-learner. Most of things, like I don't have a formal degree in electronics. Electronics was something to me that I started as a kid, like tearing apart uh, my toys. I love to get some toys when I was young, just to tear them apart and get the electrical motors. And so basically that was my beginning of interest with electronics. And I started like as a teenager. Sometimes I fixed it like some appliance, and then I start like fixing things like our radios, tube TVs. So yeah, so this basically what was the way, like fixing small things in electronics, and always reading about it. Nowadays I work as a software engineer, so it's like related, but not entirely. Okay, so I removed the first capacitor. Is just a little bit odd, because they have like the symbols. One is kind of like a half a moon, other is a triangle, and another is like a square. So instead of say, oh, negative common, and +1 and +2, no, they put me symbols. Now I'm gonna need to have a look here to figure out which one of those um, symbols means what. One thing that is I just basically need to I just needed to figure out basically the common, the negative, because yeah, the common is joined together, so I can already like join here the two capacitor common negatives, and then I just need to find the common, because I'm gonna know that, because it really doesn't matter if it's +1 or 2. So let me do a twisting here. And what I'm gonna do is, since there is this isolator is a little bit broken, the isolator, but I really wanna keep this isolator here. It is basically like phenolite board. I don't even know how to spell this. But like this old PCBs material. So basically they use it to create this isolator for the capacitor. So basically I'm gonna use this mechanical holes here to put the legs here and keep the capacitors out of the aluminum. Otherwise, I could actually install on the back side, but then I would need to change. But like it's very populated here with wires all around the place, so I really want to keep as much stock as possible the layout, so we can move forward. So let me just tighten a little bit better with my plier. So guys, how? Yeah, capacitors. But I usually, sometimes I get like a bunch of capacitors when I know that I'm gonna need them specifically. But like because I always want to use the best of the best, and they are very expensive. Like I'm paying almost €2 for each one of those capacitors, So usually, and like I buy from TME the capacitors, and they are here in like maximum 2 days. So hi, Cat. I just prefer to order what I need because it's very fast to have them here. Thank you for joining the live stream. So, and here it's changing capacitors of this nice instrument that you already saw the picture. So I'm replacing the first capacitor, and then I go to the second one. So let me find right now what is the common here on the instrument itself. Oh, there are so many schematics. So this is the capacitor that we are working. Let me just confirm. Yeah. So this is the capacitor that we are working right now. And I already found here, because as you can see, we have a bifilar transformer. So the middle here is our positive, and the diodes are providing our rectification here and providing our negative. So I already know that those two diodes here, and this point is actually the common. So because of that, actually, I'm gonna invert the capacitor position to get they closer to the old pad. And now I'm gonna apply a little bit of solder here. I'm not totally happy with this. Doesn't sound, yeah. The thing is, like, all the wires here, they don't have a good mechanical bonding, so I think I'm gonna change my mind. I think I'm gonna place those capacitors here and make like the length shorter. Yeah, exactly. Not only 20 years. 20 years. I want to die and I want to see those capacitors working. Imagine this instrument has like more than 50 years probably. And like those capacitors, like this capacitor, this brand new capacitors, the technology is much better. So I would expect a capacitor like this on an instrument like this to last at least for 50 years, So I don't expect to change anything here for a long time. Anyways, wait a little bit. There's something that is not making a lot of sense here. Because I can see here only 2 pads. There is the common ground, and then there is, let me see if I can actually give you guys a zoom here. Yeah, actually I can, because I have just a minute, guys, because my lens is manual. So, oops. I have a horrible tripod. Like, yeah, way better. You see, yeah. I'm sorry. I should thought about this before. So what happens here is, so this is the old position, and here we have only two tabs. I wasn't speaking with you, and I didn't pay attention too much. So yeah, it makes sense because as you can see here, they are joining basically the capacitor. So I actually can join as well. So I'm gonna change this entirely. Let me unwrap those legs and change the position. So now I can make like so. I thought about getting like 4,000 microfarads capacitor, but yeah, with two we have less inductance and yeah, better filtering. So I decided to keep two, even that the capacitor is twice the capacitance. And those capacitors, I also kept attention to get like a high pulse ratio capacitor. So those are not only really good capacitor, they are also like high pulse ratio. So they should be very dependable in the long run. Okay, so now, so since this facilitates a little bit for me the things now, I'm gonna use the old strategy and solder here the legs and hope for the best. Like, if I would make like a video about this, I would probably, I don't like tantalum. The only tantalum that I usually keep are those sealed, you know, that old really good ones that they are sealed. So like in the LCR meter that I made the recap, the sealed tantalum ones, I left them alone. But if are those, you know, the orange beads, no, that ones I always replace because I'm scared of those capacitors. I don't want to then destroy my instruments, you know. So I always replace those. But yeah, if I was making a video about this, probably I would like design a PCB just to hold those capacitors, and then I would put like some standoffs, you know, to grab the wires, because yeah, I'm crazy perfectionist. So I just decided that this would be the best way to go this way. And I just found something very interesting here. Let's see if you can spot, or you will not be able. So here we have our main regulation transistor, so our linear regulation. And look here, they forgot to put solder on this wire. I just spot it, and yeah, let's, yeah, some manufacturing error on HP's assembly line. Yeah, all right. Interesting. And the instrument was working nicely. So yeah, the contact was good enough. So they didn't detect during the QA process. So now I'm gonna solder the second lead. That is our positive. Oh, no, go back there. just became like a messy blob of solder, but yeah, it's good enough for Germany. Now we go to the other capacitors. So on this case, the capacitors they are individually placed in the circuit. Why? Because we have those resistors here. So basically, first we have a 270 volts output, then we have this resistor, then we have 175, and so and so. So yeah, we can't just merge the other capacitor. I will be replacing a region number 10 to cap soon too. I recently picked up broken that on. Oh, nice. Yeah. I think it's really wise from you to do it, because especially a calibrator, it's an instrument that you get for your life, and it's really not worth to go cheap, because for like, okay, let's say you're gonna spend like 100 euros. Yeah, 200 bucks. Yeah, it's a hell lot of capacitors, right? 200 bucks. I was estimating like 100 bucks, but yeah, 200. Yeah, it's a lot. Um, anyway, you know what? No, and just having like stupid ideas here to try like to open this, because like I don't have any standoffs, because here I have a lot of leads. Let's go and see what happens. But ideally, I would like to have like a PCB to replace this capacitor holder. But yeah, I don't. So let me grab my other cutter. Okay, I found it. So this one's gonna be better. Yeah, and now we're gonna spend a few hours replacing all those tantalum caps. And try to cut the tab so I keep a track and I don't lose the wire. Yeah, first one, then second one. Sorry to block your vision, guys, but it's a task that I... Yeah, but yeah, Kat, but it's a really good investment, right? Kat has a really nice calibrator as well, but it's a fluke one, if I remember. Yeah, 5440. It's a really nice calibrator. Yeah, man, make videos, because I personally love to see restoration and repair instrument videos. So go for it. Okay, I'm gonna need to get my laptop power supply as well. Just a moment. Okay, now we are safe. 800. Oh, I needed to check your channel because I don't remember to have access to your channel. I'm sorry for that. If you have a so big channel, I really missing. I'm really missing. By the way, guys, I'm gonna post an invitation link for my Discord server. So if any of you are not there yet, I'm gonna keep. Afterwards, I'm gonna delete this invitation link because I just don't wanna keep it public. But if you wanna show up there, sometimes it's kind of quiet, the Discord server, to be honest. We don't have too much people there, and I'm usually busy. But yeah, sometimes I post a few pictures of things that I'm buying or things that I'm working on. So feel comfortable, free to access or not the server. Ah, yeah. Yeah, those legs are really killing me. Yeah, it's gonna, I don't wanna break the Phenolite PCB, but it's really hard here to access it. Let me try to. Oh, I am actually. I love especially vacuum tube instruments. Oh, sorry guys, if it's just this tripod is horrible. Yeah, I think it's better. Yeah, so and here in this section, it's almost loose, but I don't have clearance to break free the last tab. And I think I'm gonna end up, yeah. Let me try to get from other angle here with this side cutter. I have a spectrum analyzer here with tracking generator from Hotchkiss, and maybe some of you guys could help me out because I'm trying to find the service manuals from these instruments. And what happens is I got to this instrument. Initially, it had a problem in the power supply on one of the 5 volts rails, and I fixed it. And then, like the instrument, it turned it on, and I was able to operate a little bit the instrument. But after some random time, the instrument only starts to freeze. You know, the UI looks like the processor just freeze after some time. And this was changing. Yeah, I would like that Philips high voltage PSU, Cat. Absolutely. Yeah, so and at some point then the instrument just got on that state, like a black screen, it starts like to switching the relays, but like it doesn't show any image. So I guess there is some problem on the digital section of that instrument. But the problem that I'm facing is really hard to troubleshoot because there are many boards. The instrument is very complex, and I reached to Hot Schwarz, and because the spectrum analyzer is very old, they told me they don't have the service manual for that instrument anymore. I don't know, but they are the manufacturer, so they say they don't have it. So yeah, what can I do? And I cannot find this service manual on the internet. And without this, I'm basically, gone with this instrument. I got to like on an auction with a lot of instruments together, so it wasn't a lot of money. But yeah, it's a really nice instrument that I would like to put it back to work. And I can't because I can't troubleshoot that instrument without a service manual. I would need to really go through the computer on it. It's x86 based instrument, but yeah, I can't probe the buses because I really don't know, and I don't really want to spend a lot of time reverse engineering the entire thing. So okay, so I removed here the capacitor. So we have the outside here being, we have the outside here being then our common negative, and then we have our 4 capacitors here in the middle. So now, we have one of the wires here, we have a second wire here, and we have our third, that is our input, and is the highest voltage. We have this. Okay, 1, 2, 3. Okay, and this one, they are negative. So I could already join them. Okay, so let's see what I'm gonna do. And this is the voltage. Let me twist here. So yeah, so we have here the second pair of diodes generating our high voltage. And yeah, so now I need to get those 4 big capacitors. And on this case, I'm wondering if I'm gonna join. Yeah, I think it's gonna be the best way to go. So I'm gonna grab the 4 capacitors. I'm gonna place the negative in the middle, and I'm gonna twist all of them. Yeah, thank you, Andy. It's a HP-410C. It's an awesome instrument, like very unique. And the highlight for these instruments, just to recap for you, is basically this C, it can measure up to 1500 volts. It can measure AC like in a calibrated way up to 700 megahertz, up to 300 volts. And out of this calibration spec, people say that it can go up to 1.5 gigahertz. So it's kind of a very unique voltmeter. And I think it is a very nice instrument, especially if you work with power RF. If you're working with transmitters or you're planning to build any kind of transmitters, I would love to have one of those. Okay, so I'm joining. Oops, where's the camera? So I'm joining here all the negative leads. Now I'm gonna use, the reason that I didn't want to break this, because now I wanna use those holes here, those square slots, so I can pass those 4 legs, and I have isolation for them, and mechanical stability. That is the most important part. It's not looking pretty as I would like to. I'm even gonna get bored and I'm gonna make a PCB to replace this. But yeah, for now it's the best we can do. So yeah, so let's put the legs aside. I'm gonna bring the negatives to the middle. You go, you go. Let me just recheck here because I'm really scared to screw up things. All right, so yeah, so that is correct. So on this case, I'm gonna remove. No, it's not broke. Actually, I got it on eBay this week for like saying that was just for parts. Well, actually, I didn't test all the features. I only tested like the ohms meter, but like the instrument is a very pristine condition. So I imagine that it only needs calibration. So I'm replacing the capacitors, you know, because yeah, bye Deftones. Yeah, so I'm replacing the capacitors because I really don't want to run the instruments before I have them replace it. Because yeah, if like I burn this transformer because of bad capacitors, I would kill myself, you know. So it's I don't want to rewire this transformer. So let's play safe and yeah, and replace the capacitors so we can actually let the instrument heat up, because this instrument really needs to get like 15-20 minutes of on period before you start calibrate then I'm going to test each one of the ranges, and if I find any issue, I'm going to be fixing it. But yeah, first part is to replace the caps. But I already turned it on, so it lights. So I guess we're not going to have big issues with it. I can cut those legs already. I'm going to be doing this right now. Yeah. Oh, I thought you were one of my youngest viewers, because yeah, I have a very broad range of viewers. Some of them are like 17, and so I'm glad that we're reaching a so broad spectrum of people. And yeah, especially the young ones, I actually would like, you know, to provide like a fresh content as much as possible, like most enjoyable, because I would like to see more like kids interested in electronics. And yeah, so yeah, I always try to make my content at least a little bit catchy, despite a lot of times I'm like repairing old equipment, so that is not so catchy, I guess, for millennials. But I do my best. Okay, so now I'm ready to solve my first negative wire. In the center. It needs some solder. Bye. Okay, so now it's gonna work. I want the kid to get into. Yeah, exactly. Hello, Yoshi. Yeah, guys, electronics is so great. I like when I was young, I didn't have too much access. Guarding on that small PCB. This one, you mean? Yes, and this is the chopper connector. So makes totally sense that there is this guard ring here. I guess this is the input for the chopper section. And I can actually tell you that it probably, yeah, definitely it is. Let me go here. So these are the first pins that goes on that guard, and as you can see here, this is the input trace, and then it goes to this resistor here, and after here there's this high impedance standoffs, and until it goes to the photocell here for the chopper input. So yeah, definitely it's a guard ring for leakage. Well spotted, Kat. I didn't had a good eyes like you. Okay, so now I'm gonna leave the second ground as the last thing to do, because it's gonna be easier to solder the positive leads first. So I'm gonna create some tabs here where I can easily solder. The wires. And now I'm gonna put some tin there. As well. 1, 2, go there, diode. Yeah, but nowadays kids just get an Arduino, program a blinking LED, and they are already satisfied, thinking that, oh, I'm already a developer, I'm already an engineer, and I have been studying like electronics as a hobbyist for like, I don't know, since my 12 years old. And I think I know nothing yet about electronics. Okay, I think I'm gonna twist here, and I'm gonna make a little bit better for me, guys, to solder this. Sorry, I'm gonna take your view a little bit for now. I think I'm just gonna cut those old tabs because, yeah, it's such a pain to remove them from the tab. So I'm gonna leave a little bit of exposed wire. Then I'm gonna thin just the tip. And yeah, and then I can solder there. Okay, first one is done. Let's cut this one as well. Let's see my first piece of electronic was a flip-flop that flashed bicycle light bulbs. We had no LEDs. Oh, cool. But they were like automotive light bulbs or like neon. I guess weren't neons, right? Because neons need high voltage. Okay. I have one more here. Another there. Incandescent, okay. Yeah, is what I was looking for. And but how did you made it? You basically used like TTL to make an oscillator, like with inverters, or did you use like a 555? Yes. One more. Oh, cool. Very simple. So you basically made an RC oscillator. I really don't like lead-free solder. Okay, guys, last lead. Afterwards, we already can test it. Okay, I'm gonna need to. And almost finishing, guys. I'm gonna be able to show you very soon. They made the arrangement here not so good for me, so I'm having to rearrange some wires. Okay, so before there's a, where's my lab? My lab is inside my home in Germany, but I'm not German. I guess it's evident I'm not German, because what about you, and where are you from? Nice. Let me install this one as well. Ah, England. Okay, all right. Ja, ich wohne in Deutschland, aber ich spreche nicht gut Deutsch. Okay, so last lead here. So I just have this resistor flapping around in the breeze that I'm just gonna put in here. So hey, and we are done. You're German, but are you German? You are supposed to speak it better than me. Yeah. Yeah, sometimes when I'm learning German, this just makes me cry, you know? Oh, yeah. Okay, so let's put this frame back. Yeah, it's a hard language, I have to admit. But I think for us that are mostly engineers, languages is really hard. My mother language is Portuguese, and I just managed to master the Portuguese after I was like an adult, because yeah, when I was young in the school, my grades were always terrible in Portuguese, and I didn't like it at all. So was as well like lack of effort. I consider myself like a moderate smart, so if I want to put the effort, I can. Well, okay, so this is not working the way I was expecting. It's a little bit twisted. So why? Why are you twisted? I think it's the frame itself is twisted. Yeah. Electronics is music to my ears. It's the universal language. Let's give some torque now. I can't have a look in Discord right now, but I promise after the live stream, I'm gonna be there online. All right, so this is the job B done, and this is the like how it looks like now. Continues to be a nest of wires, but yeah. So first order of the business, before I put any of the boards here, I'm gonna give it a little bit of power and see if no capacitor explodes. It's our first goal of the night. So let me see if it has a fuse here, but I don't trust my luck. So let's put this leads here, and that's right. Just look into the live chat. I posted like 30 minutes ago the Discord invitation. Okay, nothing exploding. Let me check the capacitor temperatures. Okay, all right, so we are good to go. Okay, bye. Okay, so now we can turn it off. I noticed there is like a wire here with a loose grip. This one. So I'm gonna take it off and I'm gonna give a little bit of pressure on the connector. Just a tiny bit, because if I break this, no. Okay, I think it's fine. Okay, I already soaked this thing in contact cleaner this afternoon, so we should be good to go. So now I'm gonna install the panels. So I'm gonna start here on the back. Now I'm gonna give a little bit less zoom. So not perfect. Yeah, more like so. Yeah, we don't need this JBC solder station anymore. Yeah, so let's install. As you can see, like the covers are in pristine condition. I'm fairly happy with the instrument. I have to say that I paid more than I would like to admit for this instrument, but like based on the fact the instrument was in pretty good condition for my taste, I decided to go for it. No, it's not you. Wrong screw. So I think I have some longer screw here. Yeah, this one. Yeah, first, and then I have those feet. They basically slide like, and you press the button like so. Like so. Now I even can Latch it. Lead-free solder is fine as long as it's a good type. Yeah. Yeah, I never had a problem with lead-free. You know, I get that 40-60% ratio. I think for me it is the best ratio. Okay, so now I can install the side covers. Yeah. So, and here I can use the shorter screws. As Rosman always say, don't put the long screw on the short hole. Look, what a beautiful instrument. This one has a little bit of a scratch here, but yeah, it's not detrimental to the instrument. Functionality only to my pride. Hey, at least the instrument has all the screws. I hate when I get an instrument and there are lost screws. Okay, all right. So we have our main covers. Install it back again. Now I just need to slide the boards. Okay, so here, there's a trick. I need to place this cover that I removed over a tab that basically earths the tube should go. Yeah, like so. Yeah. So now the tube is fully shielded. Okay, so now we can turn it on. I'm gonna put like in DC. In any range, it doesn't really matter. As you can see, our needle here went to the, yeah, so first thing that I already did, just let me turn the instrument off, was to adjust the mechanical needle here in the 0 position. Now that I turn it on, like it's charged, but yeah, I already had this adjusted. So I'm just gonna let it warm a little bit, and we can, so I'm gonna need to get some gear right now so we can actually start checking the instrument calibration. I don't have a calibrator. Probably Cat, are you there yet? I guess when I visit you in the Netherlands, I'm gonna use your calibrator to calibrate this puppy. But for now, I'm gonna grab here power supply. So I have this linear power supply we're gonna be using only to verify the range. And first thing, no problem. Just you know, I only have DC volts and 1K and 1K standards. Okay, yeah, DC volts for me, it's like already good enough. Do you know if Marco's calibrator has AC? I would like to have AC as well, calibrated. Okay, guys, so now no AC option on his. Okay, guys, so now I'm gonna do something that for some people is a blasphemy. That is basically soak the boards in WD-40. WD-40 is excellent, especially on instruments like this, because WD basically means water displacement, and basically it keeps all the humidity out of your circuits. So your board is gonna look nasty, oily, but it's gonna protect against oxidation because no water is gonna be there. So I'm basically only the vacuum tube. I'm not gonna fill it, but the remaining of the boards, I'm gonna soak them on WD. Cool. So let's hope that he gets that option, because okay, so now I see that the instrument is getting closer to the 0 position here on the DC. Yeah, if I go in ohms, it goes to infinite. And so let's just give you a quick look here. So yeah, so if we go here and try to zero the instrument, it's not zeroing. The instrument's a little bit cold right now, so I'm not gonna change the twin pots, but as you can see, the instrument works. Let me grab some resistors so we can actually measure the different ranges. Where is that? I have a box full of resistors here. Nothing like reference type. Where is that? I never can find my box of resistors when I need them. Oh, just found them. Okay, so I have one of those Amazon. Yeah, I know. And now I see that it's like leaking WD-40. But it's great, guys. I already work in the past with electronics that were exposed to basically rain, and we used to basically soak the computer, all the boards in WD-40, and it was great because even when it happened to get water into the electronics, the WD would basically displace everything and keep the electronics safe. Okay, so let's start here. Small. So 10R. Yes, since the needle is keeping there on the high side, I'm gonna adjust the 0 on the ohms scale. Doesn't want to go lower than that. So I guess the instrument is way out of calibration. Yeah, barely changed. Or maybe the instrument really has issues that we're gonna need to find. Let me see this second 0 adjust here. Yeah, this actually is changing as well, but yeah, it's not fixing my. So basically, I'm hearing the minimum on the pot. Anyways, let's just check linearity to see if we can see something. So let's grab a random resistor here. 750 R. Let's test it and see what happens. There's an alligator clip here. Yeah, so now on 100 Rs, if I go to 1K, okay, 750, I am in, where's ohms here? This is ohms. It's saying 1K. Yeah, 750 is saying basically 1K. So yeah, way out of range. Let me grab a, so the next one would be 10K, so 7.5K. And this one says that is, yeah, 10K. Yeah, so basically the calibration, miscalibration is linear. So I guess it's really just a matter of calibration. So ohms is not accurate. So let's move to DC voltage. I guess this is gonna be more or less linear. So current limit, voltage course. So now we get the DC volts and common leads. And yeah, let me stick the, so it says 15. Okay, first things first, let's place here in plus and 1.5, 15. So let's reduce here. Okay, so let's make in a different way. Yeah, I don't have a lot of resolution on this analog power supply, so let's only start with 5 volts. So okay, so when hook it up, let me try to go in course. No, let's go fine. So my power supply says now that is 1 volt. And there is basically 1 volt. Okay, so it's looking good. Let me try to go so to 5 volts. I'm gonna place it into 5 volts actually in the multimeter and then look into in the other. Yeah, it's pretty accurate. So DC, the DC range is going nicely. So let's change it to 15 volts. Now in 15 volts, I'm basically now, my power supply is varying. I guess it's a really old power supply, so it's showing its age. It needs some love as well. But yeah, it's basically here around almost 5 volts, and there is basically 5 volts. So let's increase now to 10 volts. Yeah, 10 volts basically is almost spot on. So let's go to 15. Reduce the, yeah, a little bit out of calibration. So this power supply can go up to 30. So our next range would be 50. So let's go to 20. It's all over the place, this power supply. Yeah, I guess the pot needs some contact cleaner as well. Yeah, it's like showing 18 and it's 20. Let's go to 25. Yeah, 25, 24 there. And if we go to 30, yeah, 20 weight. Yeah, so it's a little bit off, not so much. So until now, the worst part is the ohms measurement. But like this instrument, to be really honest, I don't care too much about ohms measurement because I have like high precision, like as LCR meter here if I want to measure ohms, you know. And the voltmeter part is the most interesting part to me. Okay, so let's see. Then we have 150. And if we are in 30 and we are here basically at, it's going all over the place a little bit here. The power supply, that is, yeah, I need to take care of that. So 150, I think, is the second scale. So third, yeah, almost third. Makes sense. So also we can do AC with my HP. Oh, yeah, nice. Okay, so looks fine to me. I'm thinking here if I have, let me just place the AC probe here. I want to see if the vacuum tube is gonna hit. So let me turn off this power supply. And if I grab this common and short here, and then here I have a third trim pot to zero it. It's not warming up. Yeah, I guess it will need calibration as well because I can't zero. Is the same problem with the ohms scale. It's getting into the minimum range for me for the zeroing. So I cannot zero the instrument even if I have the probe shorted here. It's not hitting it up yet, so I'm gonna leave this for a little bit more time. I want to make sure that the tube is hitting up. Anyways, I just want to show you guys a little bit the chopper here. Let me see if, let me bring the camera closer again, I guess. Little bit more. Okay, so This is basically the core of the instrument. That's a chopper board that we see there is this section here. So here in the beginning, we have the two neon bulbs that are inside that aluminum block. And basically, we have a relaxation oscillator here. So this two neon bulbs, they keep switching between each other like a flip-flop, but they have some dead time. Is around 25% of that time. And is interesting because if you are a subscriber of Mr. Carlson's, he has a HP-400 that is the new meter one that doesn't use tube anymore. It's fully transistored, but it uses the same neon system. And because these neons, they have very specific characteristics, you can't just change. Yeah, since they need to have very specific characteristics, is you can't just replace with out of the box neon tubes. You need to find like matching pairs that are actually going to oscillate properly. So he made like LED board to replace this, and he used some like half bridge driver and basically put like the dead time on the limit to generate. So worked pretty well. So go there on his channel if you're interested in this kind of stuff. And here we have like a trim pot to adjust the frequency. If I remember in his video that was like 160 hertz the frequency for this oscillator. And then we have here the two photocells. So we have the photocell subassembly 1 and the subassembly 2. So here you can see that we have inputs and outputs, and we have half of the triode. Yeah, and it's a triode as I was imagining. We have the half of the triode here, and we have the other half of the triode here. So what this brings us is a really high impedance, because basically we are driving here in the vacuum, right, of the vacuum tube, so we don't have silicon. So this line here is really high impedance, and these photocells, they are working as switches, like a classical chopper amplifier. And what they did was neat, because we have this DC amplifier output here. They kept the second triode for the output, so they kept the same impedance characteristics of the A and B models. So it was a really smart move from HP to, despite that they basically changed entirely the schematic, they kept the input characteristics the same, and the output as well the same, and replace it here with these two transistors that are making the amplification itself. So yeah, it's a relatively simple circuit that makes the hard work. So that's it, guys. I'm gonna leave the instruments here now drying out of this WD-40. That is basically already making a lake on my table. I'm gonna need to clean this, and yeah, I'm gonna leave the instrument running here. Probably I'm gonna put the top cover. That is the top cover, and I see you the next time. Bye bye.